We'll be going on now to our last topic in Chapter 6. We're skipping a couple on division. Formulas, applications, and variation. We're going to do direct variation, inverse variation, joint and combined variation. We use formulas, as we did in an earlier section, frequently in mathematical models. Many formulas contain rational expressions, these would be fractions, and to solve such formulas for a specified letter, we proceed as when solving rational equations. So in a hydraulic system, a fluid is confined to two connecting chambers. The pressure in each chamber is the same and is given by finding the force exerted, F, divided by the surface area. Therefore, we know we could set it up as a proportion. So we want to solve for A sub 2, this one. Well, would you believe this is solved in exactly the same way we did proportions? So we could actually cross multiply here, and we end up with no more fractions, and we divide by the one we don't want on that side, the F sub 1, and there's our answer. To solve a rational equation for a specified variable, again, it's basically the same. You can pause it here if you'd like to read it or copy it into your notes. We're going to take a look at variations, and there's three basic types. Direct variation here, inverse variation, and then combined variation. Here we see in a mass transit driver earns $17 per hour. So in 1 hour, $17, in 2 hours, 34, in 3 hours, 51. So in a sense, you have a series of ordered pairs that make a nice straight line, going back to some of our work in Chapter 2. So you could set it up into a direct variation in that the earned income is equal to 17 times T. 17 being the constant of variation here. And in function notation, you could write it this way. Now, when we are doing linear functions of direct variation, you might think of the old formula, this one right here. It looks so much like slope-intercept formula, which, if you recall, get a pen going here, was y equals mx plus b, where m was the slope and b was your y-intercept. Well, I don't know if you can see it right here, but this is very similar to this part up here, where m was our slope, but now in variation, we're talking about the letter k being our constant of variation, or constant of proportionality. This would be the same formula, but in function notation. Now you're going to get a number of examples, and they're all going to be based in a similar way. And let's take a look at this one. It says find the variation constant and the equation of variation if y varies directly as x, and y equals 15 and x equals 3. So let that sink in just a little bit. And my strong suggestion is whenever you have an example like this, and it's saying that it's going to be y varies directly as x, you're going to write the basic formula y equals kx. This is sort of like the standard form for direct variation. Y equals kx. Very much like slope-intercept, but there is no b out here. So what do you do? Well, where the y is, you put 15. Where the x is, and you put the k in. That's what we're trying to determine what the k is. We put the 3 there. Now that we want to solve for k, we're going to divide both sides by 3. And we get k equals 5. So find the constant of variation. Well, the constant of variation is going to be 5. Now, what would the equation of variation be? Well, you now go back to what we started, but now you know that k is 5, and there it is. So in a sense, you're solving for k, but the key to it all, I think, is writing this down when it says y varies directly as x. This is the formula you should star. And that's what they're doing here. Now, keep in mind you can change it from direct variation in its regular form to its function form by using function notation. Okay, inverse variation. And we'll look at this here. To see what we mean by inverse variation, suppose it takes one person 8 hours to paint a baseball field for a local park district. Two people do the job, it only takes 4 hours, and so on and so forth. So you have a series of ordered pairs, but they're not in a straight line. In fact, what would the relationship be? And again, for inverse variation, if that's what you see or hear, the formula is going to be y equals k over x. That is inverse variation. So what does k equal, by the way? Well, k is going to equal, notice if we multiply both sides by x, the x's cancel out, so k equals xy. So k is always the product of your x and y values. And let's see that in action here. So it says the time t required to empty a tank varies inversely as the rate r. Again, my strong advice, every time they say it's inverse variation, write this. Y equals k over x. But notice they're talking about other letters, but it's still basically the same pattern. So let's set this one up. Y in this case is going to be t for time, equals k over the rate R, and then this is your basic formula. What you have to find out is what is K. So if a pump can empty a tank in 90 minutes, there's our 90. We still need to find out what K is. At a rate of this much. How long will it take the pump to empty the same tank at the rate of this? Well, what we have to do is find our constant of variation. Now, our constant of variation is found by multiplying the 90 by 1080. So 1080 times 90. K is going to equal 97200. So our formula then will be T equals 97200 divided by R. So our new rate is this. So 97200 divided by 1500 now. So divided by 1500. And time will be 64.8 minutes. And how did we do it? Well, again, it says it was inverse rate, and we said if it's inverse rate, this is the formula for inverse variation. They talked about time and rate. We changed our X and Y here to the proper letters. We did substitution, and then we, in a sense, cross-multiplied to get this over here, 90 times that. We found out what K was. We then wrote the equation of inverse variation, put our new value of 1500 there, and got this. Okay. Now let's see what they do here. They used function notation, which is okay. They got that. That was what K was. Set it up, and there's our answer. Okay, that was good. Now for joint and combined variations, here are the formulas. It says, when a variable varies directly with more than one other variable, we say that there is joint variation. For example, in the formula for the volume of a right circular cylinder, which is this, we say that V varies jointly as H and the square of R. So what does it look like here is our constant of variation, by the way. Think about it for a moment, and it's pi right there, because they're not saying anything about pi. So we can write joint variation, if it's direct variation, as y equals, there's our k, constant of variation, there's the original x, we're now adding a z as well. That's why it's jointly. We're adding another variable. So find the equation of variation if A varies jointly as B and C. So what are you going to do first here? Well, we're going to get to the right slide. So first, what we're going to do is write the formula. Y equals K X Z. Now, they're changing the letters. A equals K BC. So again, what we have to find here is what our constant of variation is. So we know that A is 48, so let's put that here. And then we don't know what K is. We know that B is going to be 4, and C is going to be 2. So we're going to divide now both sides by 8, because 2 times 4 is 8, so these cancel out, and we get that K will equal 6. So we want to know what is the equation of variation. Well, if we use our new letters, it's going to be A equals 6 now. We've determined that from our information, BC. So that's what we set up. They changed the letters a little bit. K is 6. So there is our equation of variation. Remember, this is joint now because there's 2 letters here instead of just 1. Now, joint variation is one form of combined variation. And suppose we have direct variation that's also related to inverse. Okay? So that's combined. We're using direct and inverse. Let's take a look at it here. And let's see if we can write it out. It says Y. Now remember, K always goes up there in the numerator. Jointly as X and Z. And inversely as the product of W and P. So we're just taking it as we read it. It's a joint variation and also a combination. Y varies jointly, so there's Y. We need the K up there. X and Z, that would be direct. And then they're saying inversely as the product, indicating we're multiplying W and P. So our Y is 60. Let's put it down here. I like this. They give me plenty of room. X is 24. Z is 5. And then W N is 2 and P is 3. So I'm just going to multiply these two together and get 6. Okay? Now, one of the things, if I want to get rid of this fraction, I'm going to multiply this 6 by this. And that gives me 360. equals 5 times 24 is 120. I'm going to divide both sides by 120. This works out nicely. So K equals 3. So the equation of variation then would be up here, y equals 3, because we have determined what our constant of variation is, xz over wp. And how did we do it? Well, we saw that it was a joint variation of direct and inverse. We sort of knew our formula. We put the information into our formula. We solved for k. We found out that k was 3, and then we wrote our equation of variation. And that's what we did. And we got that k equals 3. And there is our equation. 3 is our constant of variation. Okay, you'll be doing some practice, and I believe you'll probably have a test shortly. Good luck to all of your work. Keep in mind, I have lots of examples worked out in the additional exercises section on these YouTube videos.